So today we're going to take a look at inverse functions. We know inverses. We've been doing them. Every time you solve something, you use an inverse. For instance, if I have a plus a number, we know we subtract it to move it from one side to the next. If I have multiplication, I know I divide it to undo it. So remember, an inverse is just undoing something. So we know how to do that in pieces. But now we're going to take a look at functions in general. So as this comic strip kind of shows you, I'm going to move myself for a moment. It goes into this function as an apple and it comes out it as a lemon. So the input is apple, output is lemon. If I want to get back to apple, I need to have an inverse function. I need a function that I can plug the lemons into to come back out as apples. Okay, so its goal is to have an input, to get an output from the original function, and then be able to take that output, take whatever value that was, back into a new function to get apples again. Okay, and we're going to learn how to do that. It's actually pretty simple once you get the hang of it. And again, it's basically just knowing what are opposites, what undoes each other. So this is our do now we're going to get into in class. So I'm not going to take time right now to do it in the video, but we're going to be finding composites, which is a part of our inverse operations. It is part of this whole lesson to be able to do composites and see what they come out to, because the result of the composite is going to lead us into something. So basically, what is an inverse? An inverse is a function that undoes each other. So in fancy words, it's a function of a generic equation where the input gives you an output, and then I can plug the output in and get the original input. Okay, so again, they just undo each other. To find it, simple, we're swapping places. Whatever your variables are, switch the places of them, and then solve for the variable. So usually we have x and y. So we'll swap x and y in the functions and then get y by itself. When you do that, you can choose to either rewrite it as a new name, and they'll probably tell you rewrite it as g of x or h of x or something. Or what more commonly you're going to see is this -1 power. F to the -1 of x means inverse. That's what it denotes there. Okay, some previews of what we're going to come into. Obviously, we're going to learn how to write inverses of given functions. We're going to be able to take a look at graphs and tables and figure out how were they swapped, if they were swapped, are they inverses or not. And we're going to learn how to verify. And verifying inverses are using the composites. So again, why I had you guys do the do now that I chose. When you do a composite, the goal is to see, do you get y equals x? If you do, great. You know you did it right. You know you had inverses. If not, you move along. It's okay. Because not everything is going to have a correct inverse. Okay. And also, not every inverse is going to be a valid function. And that's okay. Don't get tied up over that. So starting by finding our inverses. So I have two done here for you. So most people change f of x to y, and that's fine. We plug in our y equals 3x minus 1, swap x and y, just change their places. Everything else stays exactly as you see it. So the 3, the equal sign, the -1, those did not move. It was simply the x and y. When you do that, the goal is to get y by itself, and you use inverses to do that. So I had a -1, I need to add 1, adding and subtracting are inverses. I had 3y, that's multiplication, I divide. They are inverses of each other. So I took one simple problem, I did the inverse of each individual part to create the overall inverse of the function, which is x plus 1 all over 3. So notice addition undid the subtraction, division undid the multiplication. The second one is given a non-linear, and it has this x is greater than or equal to 0 behind it. That piece of information is going to tell you what to focus on when you're done. We're going to only look at positive values, is what they're telling us. If they don't denote what we're looking at, then I can leave it as whatever values I get. So with x squared, when I swap their places, excuse me, I know I want a square root to undo the square. I know when I do an even root, I need plus or minus. And again, I'm going to have y equals plus or minus the square root of x, and I'm only focusing on the positive values. Only positives would give me a valid response anyway, right? I can't put negatives inside the radical here. Okay. And we're going to be going through these examples in class together. But again, we are going to solely focus on swapping the x's and y's. You can change every f of x to a y if that helps you. And from there is a literal equation, just solving for y, getting it completely by itself. Okay, the second part is taking a look at tables and graphs. So inverses, again, they swap the input and the output. Input is x, output is y. So therefore also switches your domain and range. So if this is the original function, 2x plus 3, these were my tables. Even if I didn't have this inverse function here, which I do, if I didn't have that, I know because the fact that they swap x's and y's, that the table for my inverse function will literally be the original table flipped. Okay, and I can see that here. This was my x, my top row, and it now becomes the bottom row on my y, becomes the y values for my inverse. What was the y's now becomes the x's. They swap places anytime I have to find an inverse. Okay, again, the domain was my input, the range was my output. Still, domain is input and range is output, but the values went to different parts. So what was my range in the original is now my domain in the new, in the inverse, and vice versa. What was my domain in the original is now my range in the new one. Okay, and again, the graphs of them, this is my original, here's my inverse, they are being reflected around y equals x. And it's always going to reflect around y equals x because we're swapping y and x. So no matter what, y is always going to equal x and x will always equal y. In my inverses, they'll flip places. And you can see the reflection of those. If I was to plot these points, I can see that they are equally distant from that x line, the y equals x line. So what we're going to take a look at is part of our class is if I give you a table, can I look at the tables and decide, are they inverses? And again, it's as simple as reading your x's and y's. So if I just look at A, I have -2, -1, 0, 1, and 2 in my x's. That means my inverse has to have that exact same row for the y's. And if I look in my g of x, there it is, -2, -1, 0, 1, 2. They are identical. So my x in the blue, the original, matched up with my y in the red, in the inverse. And then you just have to check, do the y's match? So the y in the original, in blue, -2, 1, 4, 7, 10, does match the x's in the new, -2, 1, 4, 7, 10. So they swapped perfectly. What was an x became a y from blue to red, and what was a y in blue became a x in my red. So again, we're just going to look at tables of values and see, did the whole thing flip? Did the x's become y's and vice versa? Now for our graphs, again, no matter if they're linear or not, so we looked at a linear one, here's some nonlinear ones. This one's a cubic, this one's a quadratic. As long as it's reflecting along this diagonal, then I know it is a function. Or sorry, I know it's an inverse function. I can look at my domains and ranges of them. Domain and range are always going to flip. So more importantly, I can see it in the square one. So in a quadratic, we know the domain's all real numbers, but the range was y is greater than or equal to 0 because everything has to be above that 0 line in this original graph of quadratics. Now, when it flipped, kind of turned on its side with the inverse, the domain now becomes the range. So the domain of all real numbers in the original becomes a range of all real numbers in the inverse. And the range, which was y is greater than or equal to 0, now has to go into the domain part. Well, domains always have to go with x's. So you know you have to also swap here, x and y. So x is now greater than or equal to 0. Okay, so once I know the original domain and range, remember I'm going to flip them because that's all inverses are. We're just continually flipping them over and over and over again. So we'll take a look at graphing each of those and seeing if we notice, are they functions or are inverse functions or not? Are they following that y equals x diagonal line reflection? Okay, and these are actually the answers to those. So you can see the graphs of the previous problems. And yes, they are all reflections. You can see the different styles depending on the function that you're doing. So we're not always looking at linear. We're not always looking at quadratic. We're going to have the different roots, powers, polynomials going on here. But as long as we can follow a diagonal line, y equals x, straight through the 0, if it looks like it mirrors through that diagonal, we know we have inverse functions. Okay. We do have a horizontal line test. So if you don't want to graph it, if you want to figure out if your inverse is going to be a function or not, you can do a horizontal line test. If it hits it at only one spot, then that means your inverse is going to be a function. If it hits it in more than one spot, like we see here, your inverse is not going to be a function. That means they're going to share y values, and functions don't do that. They don't share, they're going to share x values. We know that functions don't share inputs. Okay, so again, we're going to take a look at some of these graphs and determine, would their inverses be functions? We're not going to actually find them. We're just going to determine, would it be a legit function or not? Okay, and the last thing we're going to take a look at is verifying these functions. So verifying, we're using our composites. If I take the one function and I plug it into the other, do I get x? That's the goal. If I plug it in and I can simplify it to x, that means that this process will work. Putting in the apple, getting a lemon, and putting the lemon into a new function, getting that apple back. If it does not equal x, then they're not inverse functions. And that's okay. Just move along. They're not asking you to find it. They're just asking you, are they? So in this case, the function is an inverse function. When I take 3x minus 1 and I put in x plus 1 over 3 into it, when I substitute it in, I do the composite work, I get an x. I know it works. When I go the other way, when I take 3x minus 1 and put it into x plus 1 over 3, simplify it all out, I do get an x. So yes, these two end up being functions. So that's what we're going to practice. Also, seeing if f and g are functions. If I plug it in, does it cancel out to x? If so, great. If not, then you say no and you move along. Okay, so again, we're going to be going through a bunch of these examples. If needed, I will post a video of me going through each examples as well.